The original Game Boy, launched in 1989, arrived to mixed reviews. Today, its success is a cornerstone of cultural memory, but at the time, it was seen as technologically inferior. Designed as a cheap, low-powered portable gaming system, it faced significant limitations: no screen backlight and severely limited memory for game development. Reviewers at the time criticized these features, yet these very compromises were the key to its triumph. The Game Boy was a console for the masses, and despite its constraints, engineers and programmers devised ingenious methods to create games that have endured, launching some of the most valuable franchises in entertainment history, spawning TV shows, movies, toys, and even theme parks. This is the story of the Nintendo Game Boy's remarkable engineering. The Game Boy's simple design drew heavily from its predecessor, the Nintendo Entertainment System, NS, with a familiar controller layout. Nintendo prioritized size and weight to ensure portability. At just under 15 centimeters tall and 3 centimeters thick, weighing only 220 grams, it was nearly half the size and weight of competitors like the Sega Game Gear. Even today, this 35-year-old console feels compact compared to the bulky mobile phones of its era. Nintendo's focus on user experience, an ethos that continues to define the company, was evident from the start. But how did they make the Game Boy so small and light? A major technological challenge in the early 1990s was battery life. These large, non-rechargeable batteries were expensive, so minimizing their use gave Nintendo a competitive edge. The Sega Game Gear required 6 batteries while their Game Boy used only 4, making it more compact and cost-effective. The Game Boy's batteries also lasted significantly longer. The Game Gear's 6A batteries supplied 4.5 watts, draining in just 3 hours at a cost of about $2.30 per hour of gameplay. In contrast, the Game Boy's 4 batteries delivered up to 30 hours of playtime, costing just 16 cents per hour. For a kid in the 1990s, explaining the need for new batteries every 2 weeks to a parent was tough enough. For Game Gear owners, it was nearly a daily expense. Nintendo's success hinged on recognizing and working around this limitation. While the Game Gear boasted a power-hungry, fully lit color LCD screen, the Game Boy opted for a monochrome screen displaying 4 shades of green, unviewable in darkness without a backlight. Though the Game Gear earned praise for its vibrant display, the Game Boy won consumers with its low power consumption of just 0.7 watts. However, this low-powered screen nearly derailed the entire project. Early LCD screens used a passive matrix of electrodes to control a pixel grid, with liquid crystals sandwiched between perpendicular polarizing filters. At rest, these crystals twisted light from a backplate, allowing it to pass through. When voltage was applied, the crystals untwisted, reducing light transmission. Early Game Boy prototypes used 90-degree twist liquid crystals, which untwisted gradually with voltage, producing subtle light changes. This created low contrast, especially in passive matrix displays where voltage leakage blurred neighboring pixels, worsening the image, particularly from side angles. When Nintendo's president, Hiroshi Yamauchi, tested a prototype with these screens, he canceled the project. A breakthrough came in the late 1980s when Sharp developed super-twisted pneumatic LCD screens. These used crystals that twisted between 180 and 270 degrees, enabling a sharper transition between on and off states with smaller voltage changes. This resulted in crisp black and white pixels, with the Game Boy's green tint stemming from the polarizing filters. To create 4 shades of green, the Game Boy pulsed pixels on and off at varying speeds, faster for darker shades, slower for lighter ones, a technique similar to LED dimming, imperceptible to the human eye, but detectable by cameras. The quest for affordability imposed other limitations. The Game Boy's 8-bit CPU could handle only 64 kilobytes of memory, less than a single frame of a modern video. Programming games like Super Mario Land with such constraints demanded creative solutions. The Game Boy's functions, math, and logic relied on reading or modifying these 64 kilobytes, some from the console itself, others from the game cartridge. For instance, 48 numbers read from the cartridge at startup formed the iconic Nintendo logo. By converting these numbers to binary and mapping them to pixels, the logo emerged. During boot up, the Game Boy compared the cartridge's logo data to its internal copy, bit by bit. A faulty connection would prevent startup, leading to the universal trick of blowing on the cartridge to clear dust, a practice that became a global tradition among kids. Using the Nintendo logo for this check was deliberate, forcing unlicensed developers to display a trademarked image, risking legal action. Rendering graphics with such limited memory was another challenge. Addressing each of the 160 by 144 pixels individually would require over 23,000 numbers, consuming 35% of available memory. Instead, the Game Boy used just 12.5% by employing tiles 8 by 8 pixel squares. In games like Super Mario Land 2, the CPU assembled a 32 by 32 tile background, but the screen displayed only a 20 by 18 tile viewing box. This box moved across the background for smooth scrolling, with a local coordinate system for static elements like scores. Movable objects called sprites were 8 by 8 tiles that could be flipped or rotated. Larger characters like Mario required 4 sprites. The Game Boy rendered frames line by line in a process called line scanning, inherited from the AS's cathode ray tube compatibility. Programmers could pause scanning mid-frame to adjust the viewing window, creating effects like the scrolling intros in games like Link's Awakening or curves in racing games. Audio design was similarly minimalist. The Game Boy single speaker used 4 channels, 2 square wavetone generators, 1 white noise maker, and 1 for custom waveforms from the cartridge. By combining frequencies and timings, developers crafted iconic soundtracks, like the theme still vivid in players' memories. Adding a chip triangle wave and white noise for percussion created the nostalgic chiptune sound. Games required more than visuals and audio, they needed data for logic and storytelling. Of the 65,000 numbers the Game Boy could read, only half came from the cartridge. Simple games like Tetris fit within this 32 kilobyte limit, but larger games like Red and Blue, with 373 kilobytes, used memory banking. Data was divided into 44 banks with a chip in the cartridge switching between them dynamically. For example, opening the access bank RB for decryptions, while an visit pulled prices from bank 11. This seamless switching enabled complex games within the hardware's limits. Nintendo's focus on accessibility defined the Game Boy. Priced at $89, it was far cheaper than competitors and less costly to operate, making it a cultural phenomenon. This player-first philosophy shaped Nintendo's later innovations, like the Wii's motion controllers, which introduced gaming to older audiences, and the Switch's hybrid design, enabling impromptu multiplayer sessions. The Game Boy was designed for a simpler era, relying on physical cartridges and link cables for connectivity. Today's devices, even gaming-focused ones, require accounts and transmit data to servers, feeding a booming data broker industry. These brokers collect public information for sale to marketers or malicious actors, contributing to rising spam and data breaches. Services like Incogni, our sponsor, simplify the process of removing personal data from these brokers. By automating removal requests, Incogni recently removed my data from 58 broker lists, reducing spam to a private email address without my intervention. For a 60% discount on their annual plan, visit their site. The Game Boy's legacy lies in its ingenious engineering and focus on accessibility, proving that thoughtful design can overcome technological limits to create enduring cultural icons.